Hello everyone and welcome to Solved, where we help you solve problems. In this video, we will be discussing how do we solve for the enthalpy departure of real fluids. This has applications in our calculations ranging from non-reactive processes up to reactive thermodynamic processes. We will be focusing more on fluid properties, meaning liquid or gas, or even the supercritical fluid phase. Let's try to discuss those as we solve this problem. Determine the specific enthalpy of steam at 3.5 megapascals, 300 degrees Celsius, using the Lee-Kessler generalized enthalpy departure chart. Compare the obtained value with that determined from other methods. Let's go ahead and solve this problem. Here we have our given for the problem as well as a representation of our given states compared to the standard state in an enthalpy diagram. In our enthalpy diagram, our standard state is defined in terms of the standard thermodynamic state of 25 degrees Celsius and 0.1 megapascals. Our given states, or the given in the problem, is 300 degrees Celsius and 3.5 megapascals. Now, there are lots of methods available for us to estimate the value of delta H. Delta H in this case, or the change in enthalpy, is simply equal to the enthalpy of our given states, which I will represent as small letter h, minus our enthalpy of the standard state. The enthalpy of the standard state is often represented as the standard enthalpy of formation for our specified compound. Since our fluid is water, we simply need to read the value of the standard enthalpy of formation of water vapor, and then we can substitute that to this equation. If we rearrange this equation, we have the enthalpy of our given state is equal to the standard enthalpy of formation plus delta H. Our duty for this problem is to determine the value of delta H. Once we know the value of delta H, we can substitute it to this equation, and since we already know the value of the standard enthalpy of formation of water vapor, we can then solve the absolute specific enthalpy of our given state. For the method I will be showing you in this video, using the Lee-Kessler generalized enthalpy departure charts, we will be defining our delta H in terms of what we can get from the chart. Let's first take a look at the Lee-Kessler enthalpy departure chart. This chart can be found in most thermodynamic books. In our x-axis, we have a logarithm scale of the reduced pressure P sub r. The reduced pressure is simply the actual pressure divided by the critical pressure of our substance. If you take a look at the y-axis, we have here the enthalpy departure. The enthalpy departure is defined in terms of H asterisk minus H. H asterisk is the specific enthalpy if we consider our substance as an ideal substance. So that is H asterisk minus H. Small h here is our absolute enthalpy all over R times Tc, or the critical temperature. Inside of our graph here, we have several lines. First, these lines with the numbers here represents our isotherms, wherein they represent values for the reduced temperature T sub r. The reduced temperature is equal to the actual temperature divided by the critical temperature of the substance. We also have the important parts of a phase diagram here. We have here the saturated liquid line and the saturated vapor line. And the point here, represented by the intersection of reduced pressure is equal to 1 and reduced temperature is equal to 1, is the critical points of our substance. In short, this chart can represent a saturated liquid, a saturated vapor, a mixture of saturated liquid and vapor, a subcooled liquid, a superheated vapor, and a supercritical fluid. With that flexibility, this graph has the advantage of being easy to use for a wide range of phases for our studied substance. All we need to have in order to use this chart is the critical pressure and the critical temperature of the substance. Going back, whenever we are using the Lee-Kessler generalized enthalpy departure charts, we have to define our delta H in terms of three terms. The first term is H1 asterisk minus H1. Our H1 asterisk in this case is the specific enthalpy of the standard states at ideal conditions, while H1 without asterisk is the actual enthalpy of the standard states. We add this to another term, H1 asterisk minus H2 asterisk. H1 asterisk again is the enthalpy of the standard state at ideal conditions, and H2 asterisk is the enthalpy of our given states at standard conditions. We can combine this term as simply delta H asterisk, wherein delta H asterisk is our enthalpy change for ideal behavior. This is simply determined as the integral of Cp dt. In this equation, our Cp is defined as an equation in terms of the absolute temperature. We simply integrate this expression for water and then we get our delta H asterisk. The final term in our delta H is minus H2 asterisk minus H2. This final term gives us the enthalpy departure of our given state. The terms H1 asterisk minus H1 as well as H2 asterisk minus H2 can be determined from our Lee-Kessler generalized enthalpy departure charts. However, in most cases, H1 asterisk minus H1 is negligibly small such that we can assume that almost always it is equal to 0. That is because we are comparing our given states, 300 degrees Celsius and 3.5 megapascal, to our standard states, 25 degrees Celsius and 0.1 megapascal. The ideal gas enthalpy of our standard states almost always mimics the actual enthalpy of our standard states. That's why our first term here becomes 0. Thus, simplifying this expression would give us delta H is equal to the integral of Cp times dt for water minus the enthalpy departure of our given state H2 asterisk minus H2. Our expression for the absolute specific enthalpy of our given state is now the standard enthalpy of formation of water plus the integral of Cp times dt. This represents the enthalpy change contribution of the ideal behavior and then minus H2 asterisk minus H2 or the enthalpy departure of our given state. Let us start by determining the value of our last term, the enthalpy departure of our given state. I have listed here the standard enthalpy of formation of water as well as the temperature function of the ideal gas heat capacity for steam. Also, we have here the critical temperature and critical pressure for water. Let us first solve for the reduced temperature and the reduced pressure. The reduced temperature is equal to the actual temperature, 300 degrees Celsius plus 273.15 to convert it to Kelvin, divided by the critical temperature, 647.3 Kelvin. Our reduced temperature is 0.9. In this type of solution, since we are relying on a graphical method of determining the enthalpy departure, there is no point in writing many decimal places for our values of the reduced temperature and reduced pressure. One decimal place is enough because our chart has reduced temperatures of one decimal place only. In the same token, we solve for the reduced pressure, that is the actual pressure of 3.5 megapascals divided by the critical pressure, 22.12 megapascals. Our reduced pressure is 0.16. Let us go to our enthalpy departure charts and determine the value of H2 asterisk minus H2. Let us first look for a reduced pressure of 0.16. Remember that our x-axis here is in a logarithmic scale, meaning this line is 0.1, the next line here is 0.2, this is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then finally 1. Okay, do not get confused in reading this logarithmic scale. Our 0.16 lies in between 0.1 and 0.2. This little tick here is 0.15, so 0.16 is somewhere in here. Next, our reduced temperature is 0.9. If you take a look at the isotherms, this dotted line here represents the reduced temperature of 0.9. We just have to look for the intersection between 0.9 and 0.16. They intersect somewhere here. Let's try to read the value of our enthalpy departure in our x-axis. In our vertical axis, this is 0.5 and this little tick here is 0.25. Now our point is below 0.25, so let's just call that 0.2. Let us say that our enthalpy departure is 0.2. That value of 0.2 is equal to H2 asterisk minus H2 over RTC. From the knowledge of the value of the x-axis from our Lee-Kessler generalized enthalpy departure chart, we simply have to rearrange this expression in order for us to solve for the enthalpy departure of our second state. This is 0.2 times RTC. Substituting, we have 0.2 times R. that is 8.314. This is in joules per mole per Kelvin. And we multiply it by the critical temperature 647.3 Kelvin. Our H2 asterisk minus H2, or our enthalpy departure for the given state, is equal to 1076.33 joules per mole. We now have the third term as required in our derived equation. Next step, let's solve for the second term. The second term is simply the integral of Cp times dt. For that case, I have already written our Cp, temperature with respect to temperature. This is for steam. Now take note that this specific heat equation is given as kilojoules per kilogram per Kelvin. So we do need to convert from kilograms to mole so that later we will have consistent units. The limits of integration of our heat capacity in this case will be from the standard state of 25 degrees Celsius in Kelvin, that is 298.15 Kelvin, up to our given temperature of 300 degrees Celsius or 573.15 Kelvin. At this point, you have two options. Either you manually integrate our expression for Cp with respect to temperature, which is just easy because this is just a polynomial function, or we can directly substitute that into our calculator. Most modern calculators have the integral function ready. So in this case, our x represents our temperature. Let's substitute. We have 1.79 plus 1.07 times 10 raised to negative 4 times temperature, that is x, plus 5.86 times 10 raised to negative 7 times temperature squared, minus 2 times 10 raised to negative 10 times temperature raised to the third power. Our limits of integration, 298.15 Kelvin up to 573.15 Kelvin. Our second term, integral of Cp dt, is determined to be 531.67 kilojoules per kilogram. Let's convert this to kilograms per mole. So for every 1 mole of water, you have 0.018 kilograms. Multiply by 0.018. Our integral of Cp dt term is equal to 9.57 kilojoules per mole. We now have completed the required terms in order for us to determine the absolute enthalpy of our given states. If we go back, you see here that our absolute specific enthalpy at 300 degrees Celsius and 3.5 megapascals is equal to the standard enthalpy of formation of water plus the integral of Cp dt minus the enthalpy departure term. Let us combine all of those terms and solve for the enthalpy. The standard enthalpy of formation of water is given here, that is negative 241.826 kilojoules per mole, plus the integral of Cp dt, 9.57 kilojoules per mole, minus our enthalpy departure for the given state, that is H2 asterisk minus H2. Converting this to kilojoules per mole, that is 1.07633 kilojoules per mole. Our absolute enthalpy at 300 degrees Celsius and 3.5 megapascal is now determined to be negative 233.33 kilojoules per mole. This is the value we get when we consider the Lee-Kessler generalized enthalpy departure charts for simple fluids. Let's try to compare this value with all of the other methods that we can use to estimate the absolute enthalpy. Here we have a table comparing our obtained absolute enthalpy value using the Lee-Kessler enthalpy departure charts compared with those obtained from the ideal gas assumption. Under the ideal gas assumption, I'm showing here 3 different methods. Method 1 is what we performed in this example to determine the contribution of the ideal gas enthalpy change into the overall enthalpy change. For method number 1, we have negative 232.26 kilojoules per mole, which is only 0.46% away from our real gas behavior enthalpy. Method number 2 is simpler than method number 1 because we are using the average heat capacity value such that our delta H equation becomes Cp average times delta T. The CP average is evaluated at the average temperature between the actual temperature of 300 degrees Celsius and the reference standard temperature of 25 degrees Celsius. That average temperature is 435.65 Kelvin. This method gave us a value of H equal to negative 232.27 kilojoules per mole, which is very close to what we have obtained from method number 1, in which we integrated the temperature function of the heat capacity. The percent difference of that from the real behavior is 0.45%. The third method, which is the simplest under the ideal gas assumption, states that delta H is equal to Cp naught times delta T. Cp naught represents the specific heat of steam at standard conditions, that is 25 degrees Celsius. Using that constant value of Cp, we obtain the value of the absolute enthalpy as negative 232.56 kilojoules per mole. That is only 0.33% away from the enthalpy we have determined assuming real behavior using the Lee-Kessler enthalpy departure. What you are seeing here is the enthalpy departure accounts for a small contribution in the absolute enthalpy of our non-standard state. Furthermore, this means that even if you do not account for the enthalpy departure or the real gas behavior, you will not incur a large percent error by assuming that your system is an ideal gas. However, this is only true for mild temperatures and pressures. As we increase our temperatures and pressures, we expect the enthalpy departure to also increase. The enthalpy departure has its largest values in the subcooled fluid region. Nevertheless, for more accurate values of the actual enthalpy, which is useful for determining the amount of heat transferred or the amount of work done, the Lee-Kessler enthalpy departure chart simplifies that process. That ends our discussion. Thank you for listening, and this has been another problem solved.